For over a century, a single number has defined the ceiling of human ingenuity in mechanical engineering. The internal combustion engine, the machine that built the modern world, that moved armies, built cities, and shrank continents, has never, in its entire 140-year history, managed to convert more than half the energy locked inside a drop of fuel into actual motion. The rest is simply lost, burned off as heat, wasted, gone. Toyota spent 20 years and billions of dollars trying to push past 41%. They never made it. In April of 2026, in a convention hall in Beijing, a Chinese automaker did it in a sedan that starts at $9,000. The number they posted? 48.41% thermal efficiency. Verified, certified, and entered into the Guinness World Records as the highest thermal efficiency ever achieved by a mass-produced automobile engine in history. This is not a story about a car. This is a story about who controls the next half-century of how the world moves, and why the answer to that question may already be written. Part 1. The Weight of Inefficiency. To understand what just happened, you have to understand what we have silently accepted for generations. Every time you fill your tank and turn your key, the engine under your hood converts roughly 30 to 35% of the fuel's chemical energy into forward momentum. The other 65 to 70%, it escapes through your exhaust pipe as heat. It radiates off your engine block. It dissipates into the air around you. For every dollar you spend on gasoline, you are, in effect, throwing 65 cents directly into the atmosphere and receiving nothing in return. This is not a flaw that was recently discovered. Engineers have known about it since the days of Nicholas Otto, the German inventor who patented the four-stroke internal combustion cycle in 1876. The laws of thermodynamics, specifically the Carnot efficiency limit, place a hard theoretical ceiling on how much work any heat engine can extract from fuel. The closer an engine's operating temperatures push against that ceiling, the more efficient it becomes. But getting there requires solving an almost impossibly dense tangle of mechanical, chemical, and thermal engineering problems simultaneously. For a century and a half, the world's most advanced engineering institutions, MIT, Stuttgart, Tokyo, Detroit, have collectively inched that efficiency number upward by fractions of a percentage point per decade. In the 1980s, the average production engine sat near 25%. By the early 2000s, the best in the industry were approaching 35%. Toyota, widely regarded as the gold standard of hybrid engineering, spent the better part of 2 decades refining its Atkinson cycle engines, and eventually pushed their Prius powertrain to 41% thermal efficiency, a milestone that earned them near-universal reverence in the automotive engineering community. That number stood as the gold standard for the better part of a decade. It no longer does. Part 2. The Farmer's Son from Zhejiang. To understand where the disruption came from, you have to go back to 1963, to a farming village in Zhejiang Province, China, a place far removed from the boardrooms of Toyota City or the proving grounds of Stuttgart. Li Shufu was born into modest circumstances in that village, the son of farmers who had little to offer beyond discipline and expectation. He did not attend elite engineering schools. He did not apprentice at a major automaker. What he had, from the earliest accounts of those who knew him, was an almost reckless conviction that problems other people considered solved were in fact still open. In 1986, at the age of 23, Li borrowed approximately $3,000 from family members and opened a small factory. He named it Jili, in Mandarin, Ji Li, which translates loosely as auspicious or fortunate. The factory made refrigerator parts. It was unremarkable. But Li was watching. And what he was watching, throughout the late 1980s and early 1990s, was China beginning to move. The country's economic opening was gathering speed. Roads were being paved. A middle class was beginning to form. And Li Shufu saw, with the clarity of someone who had nothing to lose, that China would one day need cars, tens of millions of them. In 1994, he pivoted the company toward motorcycles. The business grew, but motorcycles were never the destination. In 1997, Li Shufu announced that Geely would build automobiles. The reaction from China's established automotive industry was something between dismissal and mockery. Li had no formal engineering background in automotive manufacturing. He had no certified factory. He had no relationship with the government ministries that controlled automobile production licenses. A reporter who interviewed him around this period recalled him saying, with complete sincerity, that building a car was fundamentally simple, that it amounted to 4 wheels and 2 sofas. The engineering establishment found this either charming or alarming, depending on their generosity of spirit. Li Shufu was neither charming nor alarmed. He was building. In 2001, after years of regulatory maneuvering, Geely became the first privately owned Chinese company ever granted a government license to manufacture automobiles. It was a watershed moment in Chinese industrial history, though it drew little attention outside the country at the time. Then, in 2007, Li Shufu did something that seemed, by any conventional measure, absurd. He wrote a letter to Ford Motor Company, expressing his intention to acquire Volvo Cars. Part 3. The acquisition that changed everything. Ford had purchased Volvo Cars in 1999 for $6.45 billion, part of an ambitious strategy to build a premier automotive group, alongside Jaguar, Land Rover, and Aston Martin. By 2007, that strategy had collapsed under the weight of the 2008 financial crisis, and Ford was looking to shed assets. Volvo, with its reputation for safety engineering and Nordic design sensibility, was on the table. Li Shufu's letter went unanswered. He attended the 2008 Detroit Auto Show and sought meetings with Ford executives. He was largely brushed aside. A Chinese motorcycle-turned-automobile manufacturer with no international profile, making overtures toward one of Europe's most iconic automotive brands. The optics were not, from Ford's perspective, compelling. Li Shufu came back in 2009. On August 2, 2010, after months of negotiation, Li Shufu's Geely Holding Group completed the acquisition of Volvo Cars from Ford for $1.8 billion in cash, one of the most consequential deals in automotive history, though its full implications would take years to become clear. The acquisition gave Geely something that no amount of domestic engineering investment could have purchased as quickly: access. Access to Swedish safety engineering, access to European design philosophy, access to a global manufacturing network, and, crucially, access to decades of accumulated powertrain research and development that Volvo had conducted in partnership with institutions across Europe. Li Shufu did not treat Volvo as a trophy. He treated it as a graduate school. In 2018, he moved again. Through a complex series of open market purchases, Li Shufu quietly accumulated a 9.69% stake in Daimler AG, the parent company of Mercedes-Benz, making him the single largest individual shareholder of one of the world's most storied automotive dynasties. The purchase cost approximately $9 billion and sent shockwaves through the German automotive establishment, which had assumed its ownership structure was impenetrable to outside actors. By 2025, the Geely portfolio included Volvo Cars, Polestar, Lotus Cars, the Swedish-Chinese brand Lynk & Co., the Malaysian automaker Proton, and a joint venture with Mercedes-Benz that produces the smart electric vehicle brand. Through a separate entity called Horse Powertrain, a joint venture with Renault, Geely was actively licensing powertrain technology to Western manufacturers. The farmer's son from Zhejiang had, without anyone in Detroit or Stuttgart quite noticing, built one of the most globally integrated automotive empires on Earth. But the empire building was the infrastructure. The engine was the message. Part 4. The problem with the electric promise. Before we arrive at the BH15 engine and what it represents, it is worth pausing on the context in which it emerged, because that context matters enormously. For the better part of a decade, a global consensus had been quietly forming around a single thesis: the internal combustion engine was finished. The future of personal transportation belonged entirely to battery electric vehicles. The policy frameworks that followed from this thesis were sweeping. The European Union set a 2035 deadline for ending the sale of new combustion engine passenger cars. Multiple American states adopted similar targets. Automotive manufacturers, from General Motors to Volkswagen, announced trillion-dollar pivots toward electric vehicle platforms.
The logic was compelling in the abstract. Electric motors are more efficient than combustion engines. Tailpipe emissions are zero.
The energy grid, once decarbonized, would make electric vehicles genuinely clean. The future, in this telling, was both inevitable and imminent. But the actual experience of electric vehicle adoption, as it moved from early adopters into mainstream consumers, began revealing structural tensions that the policy consensus had underweighted. Charging infrastructure, in the United States and across much of Europe, remained fundamentally inadequate for the expectations of mainstream drivers. A DC fast charging session that brings a vehicle from 20% to 80% state of charge, the practical range for a road trip stop, requires between 20 and 40 minutes under favorable conditions. In cold weather or at stations with degraded equipment, the experience could be considerably longer and considerably less certain. The thermal sensitivity of lithium-ion battery packs presented a more stubborn problem. Independent studies, including data compiled by the U.S. Department of Energy's Fleet DNA project, have consistently shown range reductions of 20 to 40% at temperatures below freezing, not as edge cases, but as predictable outcomes of cold weather chemistry. For consumers in northern states, Scandinavia, or Canada, this meant that the advertised range of a vehicle bore a limited relationship to the range available during winter months. Battery replacement costs remained a significant long-term ownership concern. Depending on vehicle make, model, and battery configuration, out-of-warranty pack replacements have been quoted anywhere from $8,000 to over $20,000, a liability that sits invisibly in the financial life of an electric vehicle and surfaces only when the vehicle is aging. And underlying all of it was a grid problem that utility companies had been flagging with increasing urgency. The U.S. Department of Energy's own projections indicated that a full transition to electric vehicles at the national scale would require grid capacity additions that, under current infrastructure investment trajectories, would take decades to realize. The clean car, plugged into a grid still largely powered by natural gas and coal, delivered emissions reductions that were real, but substantially less dramatic than the marketing suggested. None of this made electric vehicles a failed technology, but it did mean that the narrative of inevitable, near-term total displacement of the internal combustion engine was, at minimum, premature. Into this uncertainty, Geely released the BH15. Part 5. The engine that rewrote the record books. The BH15 is a 1.5-liter, naturally aspirated four-cylinder internal combustion engine. On paper, those specifications are unremarkable, the kind of displacement you would find in a compact commuter car or a light commercial vehicle. What is not unremarkable is what happens inside it. The engine employs an extended Atkinson cycle, a thermodynamic approach that allows the expansion stroke to exceed the compression stroke, extracting more work from each combustion event at the cost of some low-end torque, a trade-off that makes perfect sense inside a hybrid powertrain, where an electric motor handles the low-speed torque demands. Geely's engineers paired this with a laser ignition system that delivers more precise combustion timing than conventional spark plugs, an ultra-low friction valve train, and an extremely high compression ratio that pushes combustion temperatures higher, increasing efficiency while managing thermal stress through advanced cooling and materials engineering. The combustion chamber geometry was optimized using computational fluid dynamics modeling to create near-ideal air-fuel mixing and flame propagation characteristics. Friction was reduced throughout the engine through the use of diamond-like carbon coatings on critical wear surfaces, a technology borrowed, in part, from aerospace applications. The result? 48.41% thermal efficiency. On April 15, 2026, at the Beijing International Automotive Exhibition, Geely announced this figure alongside a formal verification from Guinness World Records, which had conducted independent testing of the production engine under standardized protocols. The certification confirmed it as the highest thermal efficiency ever recorded by a mass-produced automotive engine. For context, Formula One power units, the most technologically advanced racing engines ever constructed, operated by teams with effectively unlimited engineering budgets, maintained by armies of specialist engineers between every session, and used for competitive distances measured in hundreds rather than hundreds of thousands of miles, achieve thermal efficiencies of approximately 50%. The BH15, designed to run reliably for 200,000 miles in civilian use, and sold in vehicles starting at the equivalent of $9,000, achieved 48.41% in mass production. The gap between the most advanced racing engine on Earth and a Chinese economy car engine is now, in thermal efficiency terms, less than 2 percentage points. Part 6. 106 miles per gallon and what it means. The BH-15 was not designed to be admired in isolation. It was designed as the core of what Geely calls the IHEV, Intelligent Hybrid Electric Vehicle, system, a fully integrated powertrain architecture that pairs the combustion engine with a 308 horsepower electric motor, a compact lithium-ion battery pack, and an AI-driven energy management system that Geely calls Cloud Power. The Cloud Power system uses predictive algorithms trained on real-world driving data to model the energy demands of the immediate journey, factoring in elevation changes, traffic conditions, temperature, and driver behavior patterns, and preemptively distributes load between the combustion engine and electric motor to keep both operating at their highest efficiency points as much of the time as possible. It is, in effect, a continuous optimization engine running in parallel with the powertrain. The integrated system was tested in July 2025 on a closed circuit in Hainan Province, under conditions certified by Guinness World Records. The test vehicle, a production specification Geely M Grand L Grand Sedan, a midsize family car, completed the circuit averaging 2.22 liters of fuel per 100 kilometers. Translated into American units, 106 miles per gallon. This figure requires a moment of stillness, because it is easy to read past it without absorbing its significance. 106 miles per gallon. In a production sedan. Not a stripped-down experimental prototype. Not a concept vehicle engineered exclusively for a fuel economy record. A car that seats 5 adults comfortably and sells in the Chinese domestic market at competitive prices. In 2024, Toyota, widely recognized as the global benchmark for hybrid vehicle fuel economy, drove a production Prius from Los Angeles to New York City in a real-world efficiency demonstration. That vehicle, over more than 2,800 miles of varied terrain, highway, and urban driving, averaged 92.9 miles per gallon, a figure that generated significant media coverage as an extraordinary achievement. Geely's IHEV system exceeded it by more than 14%. At the Beijing Auto Show, Geely's chief communications officer, Victor Yang, delivered a statement that, stripped of diplomatic hedging, constituted a direct industrial challenge to Japan's automotive establishment. The IHEV system, he said, would comprehensively surpass the hybrid technology developed by Japanese manufacturers. In the architecture of corporate communication, statements of that kind are rarely made lightly. They are made when the underlying numbers leave no alternative framing. Part 7. China's broad advance. Not a single company, a systemic shift. What makes the Geely announcement genuinely historic rather than merely impressive is that it is not an isolated achievement. It is the most visible peak of a range of mountains that has been rising across the Chinese automotive industry for several years. BYD, Build Your Dream, is today the world's largest seller of new energy vehicles by volume, having overtaken Tesla in total deliveries during the fourth quarter of 2023. In 2024, BYD released its fifth-generation DM hybrid system, with a documented thermal efficiency of 46.06% and a combined driving range using both its fuel tank and battery of over 2,100 kilometers, approximately 1,305 miles, on a single fill and charge. The distance from Miami to Boston is roughly 1,500 kilometers. BYD's system covers it without stopping. Aito, a brand developed through a partnership between the Chinese automaker Ceres and the technology company Huawei, achieved 45% thermal efficiency on its M7 sedan platform. Changan Automobile, SAIC Motor, GAC Group, Chery Automobile, and Great Wall Motors have each released hybrid systems in the 2024 to 2026 window, with combined ranges exceeding 2,000 kilometers and efficiency ratings that substantially outpace anything produced by American or European manufacturers. The pattern is not coincidental. It reflects a decade of deliberate Chinese government investment in hybrid and new energy vehicle research and development, channeled through a combination of direct state funding, mandatory joint venture technology transfer agreements with foreign automakers entering the Chinese market, and aggressive procurement of global engineering talent. The results are now arriving simultaneously across the industry. Meanwhile, in Japan, Toyota and Honda continue to lead their domestic competitors with hybrid efficiency ratings that have not meaningfully moved past 41%. In the United States, Ford, General Motors, and Stellantis offer conventional powertrain lineups that in their most efficient configurations approach but do not consistently achieve 40% thermal efficiency. The gap between Chinese hybrid technology and the rest of the world's production vehicles is not marginal, it is generational. Part 8. The reach of the technology. One of the underappreciated dimensions of the Geely story is that its technology is not contained by Chinese borders. Geely Holding Group currently controls Volvo Cars, which sells vehicles across Europe, North America, and Asia. It controls Polestar, the premium electric vehicle brand with significant market presence in Sweden, Germany, the United Kingdom, and the United States. It owns Lotus Cars, an iconic British performance automotive brand. It has a joint venture with Mercedes-Benz producing smart-branded electric vehicles for the European market. And through Horse Powertrain, a joint venture established with Renault Group in 2024, with Geely and Renault each holding a 50% stake, it is actively developing and licensing powertrain technology for integration into vehicles bearing European nameplates, potentially including future Renault, Nissan, and Mitsubishi models sold in Western markets. The architecture of this network means that the BH15 engine and the IHEV system that surrounds it are not technologies that will remain sequestered in the Chinese domestic market behind tariff walls. They are, in various configurations and under various licensing arrangements, already moving through the engineering pipelines of manufacturers whose vehicles are sold in every major automobile market on Earth. The question of whether American consumers will have access to this technology is not primarily a question of whether Chinese automakers can export cars to America. It is a question of whether the companies that already sell cars in America, companies with partial Geely ownership or powertrain licensing agreements, will integrate this efficiency technology into their lineups. That process has already begun. Part 9. What the numbers tell us about the future. There is a broader argument embedded in the Geely story that deserves explicit articulation, because it challenges the framing that has dominated automotive policy discussion in the West for the past decade. The proposition that battery electric vehicles represent the singular, inevitable future of personal transportation was never a scientific conclusion. It was an engineering bet, a reasonable bet based on the trajectory of battery cost curves and electric motor efficiency data available in the mid-2000s. That the challenges of range, charging infrastructure, cold weather performance, grid capacity, and battery materials supply chains would be solved faster than any competing technology pathway could mature. What the Chinese automotive industry's hybrid offensive suggests is that the competing pathway matured faster than the bet anticipated. A hybrid system achieving 106 miles per gallon uses existing liquid fuel infrastructure, the gas station network built over a century, present on virtually every inhabited road on Earth. It operates without meaningful range degradation in cold weather. It imposes no additional load on an already strained electrical grid. It eliminates battery replacement risk through smaller, less expensive battery packs that operate in a narrower state of charge window, extending their service lives significantly. And it delivers these advantages at a price point. The Geely Emgrand Grand Sedan starts at the equivalent of approximately $9,000 in the Chinese market, that no battery electric vehicle currently approaches. This does not mean electric vehicles have no future. They remain the most efficient drivetrain for short-range urban use, for vehicles operating in regions with abundant clean electricity, and for performance applications where instant torque and weight distribution advantages are determinative. The technology is real, and its advocates are not wrong about its strengths. But the argument that combustion engines have a ceiling that makes them obsolete, that 41% thermal efficiency was the end of the road, has been empirically disproven. And when an argument is disproven by a production vehicle available for purchase today, the policy frameworks built on that argument deserve re-examination. Part 10. The Man Who Built the Future from the Ground Up. It is worth returning, in closing, to Li Shufu. In 2010, when he walked out of Ford's headquarters with Volvo's title documents in hand, he was widely described in Western financial media as a lucky gambler, a man who had somehow stumbled into a transaction beyond his understanding. The consensus expectation was that Geely would strip Volvo for technology, damage the brand through cost-cutting, and eventually lose control of an asset it had no business owning. 16 years later, Volvo Cars is recording some of the strongest safety ratings in its history. Its engineering teams have contributed directly to the powertrain technologies that produced the BH15. Geely's market capitalization has grown by multiples, and the man once described as delusional for saying that building a car was simply a matter of 4 wheels and 2 sofas, is now the single most consequential figure in global automotive manufacturing that most people in the Western world have never heard of. The lesson here is not merely about one man's tenacity, though that story is genuinely remarkable. The lesson is about what happens when institutions, governments, corporations, engineering academies, decide that a problem is essentially solved and stop asking whether the solution is actually good enough. Toyota decided, sometime around 2010, that 40% thermal efficiency was approaching the practical ceiling for a production hybrid engine. They were wrong. Not because they lacked talent, not because they lacked resources, but because the assumption calcified into an institution, and institutions stop asking the questions that made them great. Geely, and the broader Chinese automotive industry, never stopped asking. In the autumn of 2025, somewhere on a closed test circuit in Hainan province, a production sedan, the kind of car a schoolteacher or a small business owner would drive to work, completed a lap averaging 2.22 liters per 100 kilometers. The Guinness adjudicators standing at trackside had their instruments, they had their protocols, they had their records going back decades, cataloging every claim anyone had ever made about what a mass-produced engine could do. They updated the record. 106 miles per gallon, in a production car, verified by the same organization that has been measuring the boundaries of human achievement for 70 years. When the Wright brothers flew at Kitty Hawk in December of 1903, 12 seconds of controlled flight seemed almost impossibly modest. But 12 seconds was enough to establish, beyond debate, that the thing could be done. Every subsequent development in aviation was built on that single proof of concept. The BH15 engine is, in its domain, a similar proof. Not because 48.41% is the ceiling. No engineer who has studied the thermodynamic space believes it is. But because it demonstrates, in production hardware at consumer prices, that the ceiling everyone agreed upon was fictional. The future of mobility will not be decided in a single city, by a single company, or through a single technology pathway. But the coordinates of that future shifted, quietly and irrevocably, on a spring afternoon in Beijing in April of 2026. The world had been moving toward the future. The future, it turns out, had been building toward the world.